This is another example of finding the orthogonal trajectory. We move this example very fast because we have already learned to find the orthogonal trajectory of a given family of curve. Find the orthogonal trajectory of the system of confocal and coaxial parabola. The example is this type of parabola is called confocal coaxial parabola. Y square equals to 4a into x plus of a. The equation given is this, having x-axis as their axis, is of the form this. So first we defined the differential equation of this family of curve. So we have to differentiate with respect to x both sides of the equation 1. It's become y dy dx equals to 2a. When we put this value of 2a here, we get the differential equation of the given confocal coaxial parabola. Exactly, for substituting this value, we get this is your differential equation. This is your differential equation of the confocal coaxial parabola. So when we find the differential equation of the confocal coaxial parabola, in that case, when you find the orthogonal trajectory of this family of this confocal coaxial parabola, you have to replace dy dx by minus dx dy. Exactly for that reason, this dy dx is replaced by minus dx dy. Since it's a whole square, so minus become plus. So here we write y dx dy the whole square. And this one 2x into dy dx, it's represent minus 2x dy dx minus y equals to 0. If we change this dx dy, if we write this one, and this one is becomes exactly, if we multiply both side by dy dx the whole square, in that case it's become y dy dx the whole square plus 2x dx dy minus y equals to 0, which is same as the equation number 1. This equation 1 and this equation 3 are the same. Since 1 and 3 are same, it's represent that when we solve this differential equation, the result should be the same with this. Okay, result should be the same with this, because the given curve differential equation is same as the differential equation of the orthogonal trajectory. So it's represent that the solution of this differential equation should be the same as the previous. So the orthogonal trajectory of this family of confocal and coaxial parabola should be y square equals to 4b plus x plus b. Just we change the parabola a to b, we get the confocal coaxial parabola. Okay, it is also very important that sometimes it may happen that in a confocal in a, when you find the orthogonal trajectory of a family of curve, it may be happen that the orthogonal trajectory of this family of curve should be the same with the given family of curve. This type of curve is known as the self orthogonal. Self orthogonal. So exactly for that reason, here we write the term those we see the system of confocal coaxial parabola is self-orthogonal. Okay, that means the given family of curve and its orthogonal are the same. That is, each member of the family of one cuts every other member of the family orthogonally. One member should cut with the other member. It's orthogonally. It's also very important example for your in kind of examination. The next part is to find the orthogonal trajectory if the given curve is in the polar form. Exactly for that reason, here we construct a diagram. Here we construct a diagram. Before we construct the diagram, you cannot understand what we want to learn here. If we consider this one is your curve and this one is your orthogonal trajectory, when the equation of the curve orthogonal trajectory is represented by OT, say OT. It's your OT, orthogonal trajectory, and this one is your curve. So if we make a tangent here, what is the meaning of the two curve is cut orthogonally is that their tangent should be the 90 degree. Okay, so if we consider this one is your pole, this one is your pole, whole, and this represent your initial axis, and the coordinate of this point is r comma theta, r comma theta, its coordinate is r comma theta. This represent r, that means this should be r according to the coordinate system, and this one should be theta. Okay, if we consider the curve, the tangent of the curve and the radius vector, this is known as the radius vector, make an angle phi. If we represent this angle is phi 1, okay, phi 1, and the radius vector makes an angle with the tangent of the orthogonal trajectory is phi 2. If we consider this, then what is the relation between phi 1 and phi 2? Phi 1 plus, because they cut at 90 degree equals to phi 2. Okay, if we consider tangent on both the side, then the left hand side becomes minus cot phi and the right hand side becomes tan phi. So this become, if we consider, if we take tangent on both the side, then it's become cot phi minus cot phi minus cot phi 1, that is equals to tan, that is equals to tan phi 2, that is equals to tan phi 2. Okay, so according to the definition, tan phi, that is known for is not known for you. So here we write the formula of tan phi, which what is tan phi? The radius vector makes the angle with the tangent is known as the phi. Tan phi is equals to r d theta dr, r d theta dr. Okay, r d theta dr. So from this we can write here r d theta, r d theta dr, it should be for the trajectory, and the left hand side becomes minus, since it's cot phi, so the result becomes 1 by r dr d theta, 1 by r dr d theta for the curve. Dr, it's d theta. Okay, d theta for curve. So when we find the differential equation of the orthogonal trajectory, first we eliminate the given curve parameter, next differentiate with respect to theta both the side, and if you want to find the differential equation of the orthogonal trajectory, in that case it's become dr d theta, that is equals to that is equals to minus r square d theta dr, exactly r square d theta dr. So exactly for that reason here we define the step to find the orthogonal trajectory of the given family of curve. The first step is the given form of the curve. Next step is to eliminate c, that is the parameter. From the curve we get the differential equation of the given family of curve. Next we replace d theta by minus r square d theta dr. How can I find? Exactly from this concept we can find the dr d theta should be replaced by minus r square d theta dr. And solving this differential equation we get the orthogonal trajectory in terms of r theta and uh, r theta and some arbitrary parameter. Okay, so this is the procedure to evaluate a orthogonal trajectory for a curve which is in the polar coordinate system. So wait for the next lecture. We will expand this using two different examples to clear your idea. Thank you for listening.